Hello everybody and welcome to this organic chemistry video for A-level chemistry. This is the final video for year 1 organic chemistry. After this we will have been through all of the different topics. And in this video we will be looking at infrared spectroscopy. We will then move on to high resolution mass spectrometry, and we will finish by looking at test tube reactions where you can do simple chemical tests to identify the presence of different functional groups. Before I move on to begin infrared spectroscopy, I do just want to highlight the different name ending for infrared spectroscopy and mass spectrometry. Now, a metric is a measurement, and so mass spectrometry means measuring, whereas scopy comes from the Greek to do with inspecting or viewing. So infrared spectroscopy, it means more viewing or visualizing. And so that's a subtle difference between infrared spectroscopy and mass spectrometry. So the name endings do indicate a difference, but in terms of your understanding for A-level chemistry, you don't really need to know why there is that difference. If you were to group mass spectrometry and infrared spectroscopy together into one term, you would refer to them as spectroscopic techniques, or perhaps analytical techniques. Our understanding of organic molecules, their structure and the way they react, has been enhanced by organic analysis. Organic analysis involves a variety of different analytical techniques, and we're going to explore two of them now, starting with infrared spectroscopy. First of all, let me explain that infrared spectroscopy is often abbreviated to IR spectroscopy for ease. And first thing I will say about infrared spectroscopy is that it is all to do with the absorption of infrared radiation. And the statement that I've got written here comes from the spec directly, that the molecules have got bonds, and that some of these bonds in the molecule will absorb infrared radiation at characteristic wave numbers. Now obviously this bears a bit more of an explanation, but the core idea of infrared spectroscopy is that infrared radiation is being absorbed, and this gives us information about what bonds there are in a molecule. There are actually different types of infrared spectroscopy, but you don't need to know the subtleties of how each one works, you just need to know the core idea. And the core idea is that you have infrared radiation coming from a source. The infrared radiation then hits a sample, and some of that infrared radiation passes straight through. Some of it is absorbed almost completely, and some of it is absorbed partially. The radiation that passes through the sample is referred to as transmitted radiation. This radiation will then hit a detector, and the detector will be connected to a computer screen, and it's that computer readout that we will see as our infrared spectrum that I'm just going to sketch will look something like this, a series of spikes going down. I'm just going to take a moment to remind you what infrared light is by taking you back to GCSE physics. If you remember the electromagnetic spectrum, where you have got all the different types of light, you've got radio, you've got microwave, infrared, visible light, ultraviolet, X-ray, and gamma rays. So those are all different types of light. And the radio have got long wavelength, and gamma is short wavelength, and radio have got low frequency, and gamma have got the high frequency, high energy. Now visible is a very, very small part of this, and a good way to visualize this is to think about one octave on the piano, a series of your 8 notes where you return back to your original note. But just to represent it by a narrow band, that would be the visible part of the electromagnetic spectrum. In contrast, infrared is 4 or 5 times longer and wider than the visible part of the spectrum. And what that means is, to bring it back to infrared spectroscopy, that this infrared radiation that goes into the sample has got a range of different frequencies or a range of different wavelengths. And so we zoom in on what has been absorbed, and we can make deductions about what is present in the molecule by learning what type of infrared radiation, what frequency of infrared radiation gets absorbed by the sample. I want to explore a little bit more deeply the absorbance of infrared radiation. This absorbance depends on two things. It depends, as you can see here, on bond polarity and on molecular vibrations. Now let's start with bond polarity, because that is not new. A polar bond is one where you have got a partial positive and a partial negative. And a good example might be a carbon bonded to an oxygen, or a hydrogen bonded to an oxygen, something, crucially, that is very electronegative compared to the other atom that it is bonded to. And this holds true for double bonds between carbon and oxygen as well. Now, the absorption of infrared radiation is significantly stronger if you have got a polar bond. So all of these bonds here would show up as very, very strong peaks in the infrared spectrum. In contrast, things such as carbon-to-carbon single bonds, which are non-polar, they hardly show up at all. And for A-level chemistry, we can pretty much consider that they don't show up. And similarly, carbon-to-hydrogen bonds are almost totally non-polar, not entirely. And so these are considered to be weak peaks. And the only reason that sometimes the C to H peak is actually quite big on an infrared spectrum is that there are lots of these bonds. So lots and lots of these weak peaks will add together to give a stronger peak. So that's one aspect of infrared absorption. A polar bond will absorb infrared radiation much better than a non-polar bond. And the second aspect of this is very leading. The implication here is that molecules are vibrating, and most specifically what we mean here is that if you consider a pair of atoms such as carbon and oxygen in this bond here, they don't have a fixed position and bonds don't have a fixed length. What is happening all the time is that the bond might be stretching, and so the carbon and the oxygen get further apart, or they might compress and move to a shorter bond length. So this is called a stretching vibration, and this corresponds to an absorption of infrared radiation. Alternatively, molecules can do other things as well as compress and stretch. They can bend, and they can scissor, they can twist, and they can rock, and all of these are different types of descriptions of the vibrations that are happening in molecules. What we need to know for A-level chemistry is that these vibrations exist. We don't need to know all of the names. I suggest you just think about this one type, which is stretching, which is where the carbon and the oxygen are getting further and further apart and then closer together on a temporary basis. Let's move on now to take a look at what an infrared spectrum actually looks like. First of all, on the y-axis, we have got transmittance, which is expressed as a percentage, and so we have 100 at the top. So if nothing was absorbed at all, everything would be transmitted, and so we would have one flat line along the top. For the x-axis, we have wave number in centimetres to the -1. Wave number, which is proportional to frequency, is preferred to frequency for a couple of reasons, but the most significant of which is that it makes the numbers easier to understand. frequencies can be absolutely tiny and also absolutely massive, whereas when we use our wave numbers, we get a band that goes between 0 and 4000. A curiosity of these spectra is that even though it looks like a graph, the numbers work backwards. So we've got 4000 at one end and we have got 0 at the other end. And as I say, a typical spectrum will have peaks between these two numbers. Let me sketch one now and just make something up. And so here we have an infrared spectrum that I have just sketched, and you can see that what I've tried to do here with this made up spectrum is have a slightly wobbly line around about 100% for most of the spectrum. There's a little dip here around about 3000, but we can ignore little dips. What we're interested in most here is this absorption here. And what you would do in an exam situation is you would track where that absorption is, get down to the x-axis and find out that this is round about 1680. And so obviously in an exam you would have a better scale and you'd have a ruler to measure this. And you would look up on your data sheet, and the data sheet has got a list of all the different characteristic absorptions, so you don't need to memorize any of them. And what you would find out when you looked up on your data sheet is that this is characteristic of a C to O double bond that you would commonly find in aldehydes, ketones, carboxylic acids and esters. And so this 1680 centimetres to the minus 1 has given us an identity of what functional group is present. There's also an interesting region towards the right hand side with lots of tiny peaks, and this region is called the Fingerprint Region. More on this later. If we take a look at this new spectrum that I've drawn, you can see that the most interesting peak by far is this one on the left hand side over here. And if we track this peak down to the x-axis, we find that it is around about 3400 centimetres to the minus 1. If we take a look at this on the data sheet, we find out that this corresponds to an oxygen being bonded to a hydrogen, and that specifically this bond is found in alcohols. And you can recognise that by the fact that this peak is one that is particularly broad. In other words, it's more stretched out and less spiky seeming than some of the other peaks that we get. And I've been saying it, but I just want to identify the fact that we call these peaks even though they're going downwards and look more like troughs. We still call them peaks. So the major peak in this spectrum was for an alcohol in this molecule. Something that's slightly peculiar in this new spectrum is that we end up with a really wide looking peak on the left hand side, and the reason for that is that this is actually two peaks that overlap with one another. And if we track the left hand of the two down to the x-axis, we can see that we've got an O to H bond of round about 3000 centimetres to the minus 1, and that corresponds to the OH group. And I said that the peak for the OH bond was very broad, but what we have here is we have an OH group found in carboxylic acids, and that coincides or overlaps with this region on here, which is for the C to H found in a variety of organic molecules. And so the broad peak for the OH acid ends up looking more spiky because it overlaps. We've got further confirmation that this is a carboxylic acid if we look to the right and we take the peak and track it down to here, and we find that we have got 1680 centimetres to the minus 1, which is C double bond O. So we have identified the fact that it is a carboxylic acid. We've got further proof that it is because it's got the C double bond O group there as well. So we have proven that we've got this functional group present. So I hope that has given you a good appreciation of the fact that you end up with different peaks in different parts of the spectrum, and this coincides with an absorbance of infrared radiation of a particular frequency by a characteristic bond that corresponds to that frequency. There are, of course, others You don't need to memorize any of these bonds and their wave numbers. You just need to be able to use them in an exam. Not only can infrared spectroscopy be used to identify the functional groups present in a compound, it can also be used to assess how pure a compound is and identify any impurities that are present. And the reason for this is twofold. First of all, if this ethanoic acid or carboxylic acid sample was contaminated with something, we might get an additional peak in a different part of the spectrum. And I've chosen this part on here because this is an approximation of where you find the oxygen to hydrogen bonds in water. And so this is interesting because it raises the point that alcohol bonds, OH bonds in carboxylic acids, they're found over here, but in a different molecule, they are found in a different part of the infrared spectrum. So that's surprising. You would expect OH bonds to be over here, but in water you find them in a different position. So that's one way that we can detect impurities. Another way is in the fingerprint region, because if this was the fingerprint region over here for a particular substance, a particular carboxylic acid, you would find additional peaks in the fingerprint region, and some peaks might be bigger and there might just be extra peaks over here. And so the fingerprint region would be different if you had an impurity. In some respects, infrared spectroscopy is not as useful as some of the others because the information that you get from it tells you what bond or what functional group is present in a molecule, but no more information than that. However, there is one last part of the infrared spectrum that is phenomenally useful if used correctly, and that is the fingerprint region that we mentioned earlier. Now, the fingerprint region is in the region of 1500 centimetres to the -1 down to around about 500 centimetres to the -1. And the first really important thing to mention about the fingerprint region is it is entirely unique. So that means that for a pure substance, no two fingerprint regions will be the same. And so what that means is that there are computer databases that store infrared spectra of thousands of organic compounds. So you can check and compare relatively quickly using a computer. In an exam situation, you might be asked a question such as the one here. How could you prove that this was a spectrum for propanal and not for any other aldehyde or ketone? And the answer to this question comes in two parts, and it could be a 2-mark answer. And the first mark would be for saying that we would need to compare the spectrum for our unknown substance that we suspect is propanal to a database of known spectra. And then the second mark would be for saying if we get an exact match, then this was a sample of propanal. Or conversely, if we didn't get an exact match, then we know that it wouldn't be propanal. We don't need to say both of those things, so it's more likely and more useful that we would say we would get an exact match to prove something's identity. And that's the great power of the fingerprint region, to confirm our identity of our unknown substance. The final aspect of infrared spectroscopy that we're going to explore now at first glance appears not to be related to infrared spectroscopy, but I hope you will see that it is. And what we're going to look at is global warming and greenhouse gases. This is something that I would expect you to be familiar with in a broad sense. You'll probably know that the sun gives out different types of light. It gives visible light that we can see, it gives infrared radiation that keeps us warm, and it gives ultraviolet radiation that we can't see, but we know we need to protect ourselves from using sun cream. So all of these different types of radiation travel through the vacuum of space because they don't need particles, and they reach us from the sun. Now, we have got around the outside of the Earth, we have got our greenhouse gases, and the greenhouse gases are carbon dioxide, water, and methane. Now, the infrared radiation that comes from the sun is short wavelength infrared, and that isn't absorbed by the greenhouse gases, so it passes straight on through and hits the Earth and warms it up. This absorbed infrared radiation is then re-emitted by the Earth as longer wavelength infrared radiation. The significance of this is that the longer wavelength infrared radiation can be absorbed by the greenhouse gases. Specifically, it is the polar bonds in the greenhouse gases, for instance carbon dioxide, that absorbs the infrared radiation. This then prevents the infrared radiation from leaving the atmosphere, which leads to the effect of global warming, because this heat energy, infrared radiation, is trapped and can't leave. It might be that infrared radiation emitted by the Earth gets absorbed by a carbon dioxide molecule and one of its polar bonds in it. It could be that this infrared radiation is then re-emitted out into space, or it could be re-emitted sort of sideways, and it could encounter another greenhouse gas where it could be absorbed by the oxygen to hydrogen bond this time. Or alternatively, it could be re-emitted back down to Earth, further increasing the temperature, further adding to global warming. And so the problem that we're experiencing at the moment is that more greenhouse gases are being emitted by cars and power stations, etc. And so the thicker this layer of greenhouse gases is, the greater the amount of infrared radiation that is prevented from leaving the atmosphere, because there is a greater chance that these polar oxygen to hydrogen bonds and all the other bonds in the greenhouse gases, more chance that they're going to absorb the infrared radiation, which leads to increased global warming. I should finish by saying that the wave number for absorption for the CO2, that means the carbon to oxygen bond in CO2, is different to the 1680 to 1750 range that you'll see on your data sheet. And that has occasionally been the focus of an exam question where you've been shown an infrared spectrum for carbon dioxide gas, and you've been asked a question such as, why is this spectrum surprising? And what they're thrusting towards there is the idea that the wave number is different to what you would expect for carbon dioxide. So this aspect of infrared spectroscopy is related to infrared spectroscopy, and they will pull it back to it in an exam question, but it is of course infrared radiation in a real wider world context, which is very significant. We encountered the mass spectrometer in the very first physical chemistry topic, and what we're going to do in this video is focus on the high resolution mass spectrometer rather than the inner workings of a time of flight mass spectrometer. We'll be focusing on high resolution mass spectrometry. Now, before I dive into it, let me explain what high resolution is. What you might not have noticed is that there was a cluster of dots on my screen here, and if I just circle it here just so you can see them. So if I was to ask you how many dots were there on the screen here, you might not be able to tell me the answer. And that's because we're looking at this picture in low resolution. Now, low resolution is less precise, and so high resolution is more precise. And effectively what we're kind of doing is we're zooming in on the picture. And so we've lost my title there, but we can see, I hope, that there are in fact 6 dots. I'll zoom in a little bit more so we can see that there are 6 dots on the screen. And so that is more highly resolved. We can tell the difference between those 6 dots more clearly. So I'll zoom back out and I'll just write that down. That resolution is the ability to differentiate things, so to tell one thing apart from another, or in slightly more succinct terms, it is to do with the degree of precision. Let's move on now to explore that concept in a bit more detail and so we can see exactly what I mean by the degree of precision. I think the best way to explore that is through a question. So why do we need a higher resolution? Why do we need a higher degree of precision? So what I've got here is I've got a question. What is the MR of carbon dioxide and dinitrogen oxide? The simple mass spectrometers will measure relative atomic masses to more than 1 decimal point. However, your periodic table will express values for only 1 decimal point. So if we just explore this question on here, CO2, we've got carbon, which is 12.0, oxygen, which is 16.0, and we've got another oxygen, 16.0. So the relative molecular mass of that adds up to 44 when you add all of those three together. For the dinitrogen oxide, we've got 14 for the nitrogen, and we've got 14 for the other nitrogen, and we've got 16 for the oxygen. So that's 28 plus 16, which is once again 44.0. So these two cannot be told apart, they can't be separated, we can't resolve one from another. And so if we had a container, like this one here, full of particles of a gas, and then we analysed them using a low resolution mass spectrometer, we might think that there was only one substance in there because we would find an MR of 44, so an MZ of 44 would be detected, and both of these substances have got an MR of 44. So we would think that there is only one substance in this sample. However, some mass spectrometers can measure masses to 3, 4, or even 5 decimal places. And this method allows us to work out the molecular formula of the sample with greater precision. It allows us to find out what the MR is for a substance to 5 decimal points. And so I've got some data here on the left-hand side showing the precise AR values, in other words, to not 1 but 5 decimal points. What we can see is that carbon-12 is given a precise AR of 12 by definition. Remember, that's how we define the relative atomic mass of a substance. We compare it to a 12th of the mass of a carbon-12 atom. And so if we've got CO2, carbon really is 12.0000. And then the oxygen is not 16, it's actually slightly less than 16, you'll notice. It's 15.99491. And there are 2 of them in carbon dioxide. So we need to add all of these 3 numbers together to get the precise mass of carbon dioxide. Before we even do this, we can have a sort of a reasonableness check. So we worked it out as 44 when we were working to 1 decimal point. Now that we know that oxygen is slightly lighter than 16, this means that our number should come out to be slightly less than 44. And it does, which comes out as 43.98982. So we can see that that is a little bit less than 44. For the dinitrogen oxide, we need to do the same approach. We've got 2 nitrogen atoms, and instead of nitrogen being 14 like we thought it was, it's a little bit heavier, 14.000643. And oxygen, of course, there's 1 oxygen that is a little bit lighter. So what I would expect here is, because the nitrogen is a little bit heavier, and this is on the 3rd decimal point, and there's 2 of them, and the oxygen is a bit lighter, also on the 3rd decimal point, I would expect this value to come out to be slightly greater than 44, in fact. And that's what it does do. It comes out at 44.00777. So this difference really only kicks in on the 3rd decimal point here. So it really is quite close to 44. But overall, what this allows us to do is it allows us to tell these 2 molecules apart. And so we would see in our substance, if we got some MZ values of 43.98982 or 44.00777, we would be able to say, aha, we have got 2 substances in our box, not just 1. And this approach is in fact used in exam-style questions. So let's have a look at one that I've paraphrased here. How could high-resolution mass spectrometry prove that a sample of propane gas with the formula C3H8 was contaminated with carbon dioxide? Well, this is the same principle that we were just exploring. We would want to prove that there were two substances by using the high-resolution mass spectrometer to see if we get two different MZ values. Now to 1 decimal point, remember these values are still going to be 44.0, and so that's the whole principle of why we need this high-resolution mass spectrometer, because 3 lots of 12 for carbon is 36, plus 8 gives us our 44. However, when we look at the high-resolution C3H8, we need to take 3 lots of that 12.0, which is going to be 36.50, but the 8 hydrogen, we need to add on 8 lots of 1.00794, which is going to give us a total of 44.06352. So this one is even more different from the 1 decimal point MZ value, and that's because hydrogen is quite a bit heavier than we think, and there's 8 of them in this molecule. So now we've got the MZ value for propane to 5 decimal points, we can compare it to the carbon dioxide MZ that we worked out in the previous slide, which is 43.98982. Now, obviously now we have got 2 different values, which shows that there are 2 substances in our sample. So we have our propane gas, which is the 44.06352, but we also have something else, which is carbon dioxide's MZ value. So our propane is contaminated. Now, outside of an A-level chemistry lesson or exam, you are very likely to use more than one analytical technique to identify an unknown substance. You would use infrared spectroscopy, and that would enable you to identify the bonds and the functional groups present in this unknown molecule. You would then use the mass spectrometer to determine the precise MR for this unknown substance. And in many cases, these 2 bits of information might be enough. You might find that it is an alcohol, and you might determine that its MR is 32. And then that would allow you to arrive at the conclusion that it was methanol. Other supporting information might come from combustion analysis, which, as we saw in the amount of substance topic, enables you to arrive at an empirical formula for a substance. And finally, we might choose to use nuclear magnetic resonance spectroscopy, which enables us to determine how different carbon atoms are bonded together and organised in an unknown molecule. More about NMR spectroscopy in Year 2 Organic Chemistry. We're going to finish this video by looking at some chemical tests that you can do to identify the functional groups present in an organic compound. Now, if I were to give you one piece of advice about this, I would say keep it simple. Sometimes there is more than one way of doing something, and you could be tempted to come up with a convoluted method. These chemical test methods should all be single test tube reactions, and the process of answering the questions in exams should be formulaic. You would explain what you were testing for, you would say what reagent that you would use, and you would demonstrate your knowledge of the result. And there are 5 functional groups that you need to be able to test for. There is the carbon-to-carbon double bond in alkenes. The test is nice and easy. You shake it with bromine water, and the result is that the colour changes from orange to colourless, or quite simply, it decolorizes. It does depend on what you're asked in the question, whether you're asked for the colour change or whether you're asked for the observation. Because if you're asked for the colour change, what they're asking you is to demonstrate your knowledge of what the starting colour will be, not just the final colour. The next functional group that you need to know how to test for is the alcohol, and to do that you would use acidified potassium dichromate, and you would acidify it using sulfuric acid rather than any other acid, and you would warm these chemicals gently. And the observation here would be that the orange colour would turn green, and it would do that for primary and secondary alcohols, not for tertiary. Tertiary, you would not get anything happening at all. You would see no visible change. The next test that you need to know is the carboxylic acid test, and to do this you would use sodium hydrogen carbonate either as a solution or as a solid powder form. And what you would observe is you would observe effervescence or simply fizzing. The reason for this effervescence, this fizzing, is that CO2 has been produced. I would be a little bit cautious about saying that for my result though, that CO2 was produced. I would stick to the effervescence, because if you look at a test tube and see it bubbling away, you don't know that CO2 is being produced, you only know that a gas has been produced. And so to prove that CO2 was being produced, you would then need to bubble that gas through lime water and have it go cloudy. The fourth chemical test that you need to know about is the aldehyde test, and there are two different strategies here. You could use Fehling's solution and warm it, and what you would observe in this instance is a blue solution changing to a red precipitate. And this is the exact same observation as in biology when you are testing with Benedicts for reducing sugars, and that's because the active ingredient is copper 2+ in Fehling's and in Benedict's, and when you get your red precipitate you get copper 1 oxide produced, and that's a red solid. The other test for aldehydes is Tollen's solution, and in this case you get a silver mirror forming. And this silver mirror is literally the chemical silver, and you would only get that for an aldehyde. This is probably a good moment to point out negative proofs. Aldehydes are often grouped together with ketones because they are functional group isomers, and for ketones you would see no visible change at all if you were to do Fehling's or Tollen's tests. The final functional group that you need to know how to test for is halogenoalkanes. The chemical that you add to this is acidified silver nitrate. This time, when you are acidifying the silver nitrate, you should use nitric acid for the reason that the nitrate ion is present in the silver nitrate already. And so we know it isn't going to interfere with any of the chemical tests. After we had added our silver nitrate, we would observe a precipitate of silver halide. Now that might be white, which would indicate silver chloride, it might be cream, which would indicate silver bromide, and it might be yellow, which would indicate silver iodide had been formed. And then we would work backwards and say, okay, well this was chlorobutane or iodopentane, depending on the colour of the precipitate that we see. Now the slight problem is that cream and white are very, very similar, and so we would do a second step, and that's why I had written a number 1 next to my silver nitrate. And step 2 would be to add dilute ammonia solution to our precipitate. And what would happen then depends on the colour of precipitate that we'd already seen. If we had a white precipitate already, this would dissolve. If we didn't see a precipitate dissolving, what we might do then is we might add concentrated ammonia solution to our precipitate. And then, in that instance, what we would observe is the cream precipitate would dissolve, and the yellow precipitate would most likely do nothing or potentially change colour ever so slightly. And so, because cream and white are similar colours, we might need to do step 2 or step 3 for the proof of whether it was cream or whether it was white. And on the subject of white precipitates, why do we need to acidify at all? Well, silver from the silver nitrate can react with carbonate impurities that we find in all sorts of different samples and make silver carbonate, which is a white precipitate. And so we might get a false positive where we think we had chloropentane, but we actually didn't. We just had pentane with carbonate impurities. And so the purpose of the acid is to provide the hydrogen ions that all acids provide to react with impurities such as carbonate ions and turn them into water and carbon dioxide. And those chemicals aren't going to interfere with our chemical tests and give us any false positives. So that's why we need to acidify our silver nitrate. And we use nitric acid rather than something like chloride ions, because chloride ions would obviously also interfere with the test by giving us a white precipitate with the silver ions. So we use nitric acid because it doesn't have any ions that would interfere with the test. We're going to finish this video by looking at 3 exam-style questions that you could easily be asked. And so this first question is the most simple type of question that they could ask. We are presented with a pair of test tubes, which they wouldn't draw in the exam. They would give lengthier explanations of the question, but I'm just drawing the 2 test tubes here, and I'm labelling them A and B. And I'm giving you some information. Chemical A and B, one of them is an aldehyde and the other is a ketone. And the question is, how could you tell A and B apart, or how could you distinguish between A and B? And these will almost always be a 3-mark question, where mark number 1 is what you would do or what reagent you would add. This part could vary ever so slightly depending on what they're asking you to tell apart. Here they wouldn't ask for a reagent because there are 2 things that you would need to say. You would need to say, I would use Tollens, or you could use Fehling's, but you would also warm it. So simply asking for the reagent is not appropriate here. So we'd need to say we'd need to have Tollens solution and we would warm it. And then you would follow up by saying, okay, the aldehyde would give a silver mirror. And then the ketone, this is a 3rd mark, would give no visible change. And so as a result of that, we are able to distinguish between chemical A and chemical B, because the one that gives no visible change is the ketone. The one that gives the silver mirror is the aldehyde. The second type of exam question is similar in appearance to the first, but significantly more complicated. So the reason that it's more complicated is that they introduce a 3rd chemical. And so, for instance, we've got propanal, propan-1-ol, and propanone. And so your command is, how could you find out which is which? And this might be 5 marks, or it might even be 6 marks if they're feeling generous. My big piece of advice here is to consider this as if you were telling a story. And so you would need to say, I would start by, and describe what you would do. And then you would say, and then I would. And having this structure really helps you make sure you don't miss anything out. So the first thing that you need to recognise is that you have got distinctive functional groups. So for instance, we've got an aldehyde. We know that aldehydes will give a silver mirror with Tollens. So you would need to say, I would start by adding Tollens solution to samples of all 3 unknowns and warming. And then you could say the one that gives a silver mirror is propanal, and that the others would give no visible change. And so we have identified propanal from our 3. And so the then I would section is really, how would you tell apart propan-1-ol and propanone? And propan-1-ol is a primary alcohol, and so that's going to be the acidified potassium dichromate. And so you would say that then I would add acidified potassium dichromate to fresh samples of the 2 unknowns and warm. And then you can say that the one that goes from orange to green is propan-1-ol, and the chemical that gave no visible change would be propanone. And so we would then have distinguished between our remaining 2 chemicals. Do note that in questions like this, they do ask you to make a false proof. In other words, we are proving what something is by looking at what it doesn't do. And so that only works because we know the identities of the 3 chemicals, and propanone was named, and so it would be the one that did nothing in either of these 2 tests. Speaking of which, this question seems more complicated and it's worth more marks, but essentially what it is is two pairs of chemical tests joined together by an overarching theme. So we did the Tollens test to find the aldehyde, and then we followed up with the alcohol test to find the propan-1-ol. And so that allowed us to therefore make an inference about the third chemical by it was the one that did nothing in either of the two chemical tests. The final type of exam question that I'm going to consider is ones where you have to identify a chemical, not say how you would identify it. And so, for instance, in this question here, we are being told that chemicals X and Y both have the molecular formula C6H12. Then we're given some follow-up information where X decolorizes bromine water, and as we read through an exam question and annotate it, we need to be thinking that X therefore must be an alkene, because that's what a test for an alkene is. But Y does not, so therefore it is not an alkene. And since they've got the same molecular formula, we need to be thinking, well, these are functional group isomers. And so since we know that X is an alkene and Y is not an alkene, but it is a functional group isomer of X, we know that it therefore must be a cycloalkane. And it's for questions like this that your knowledge of functional group isomer pairs needs to be really quite sharp. Now that we know that we've got an alkene for X and we've got a cycloalkane for Y, really anything is suitable. So we're drawing an alkene. So here we go, double bond drawn, and I'm going to make it a nice symmetrical alkene that has got the formula C6H12. And so that is a totally acceptable answer, as would hex 1-ene, hex 2-ene, etc. And then similarly, the cycloalkane, ring of 6 carbon atoms that you could draw in full display like this, and then with all the hydrogen atoms shown as well. But this is a very, very lengthy method, and it's quite boring to go through because it's repetitive. And so what I recommend instead is the structural formula where you draw your hexagon. And that means the same thing. Tons faster, much easier. Just got to be sure that you draw a nice neat hexagon, so use a pencil. Another question of the same ilk is, if we've got two chemicals M and N, they both have the same molecular formula, C4H8O, and so once again, these are functional group isomers. We're told that M gives a red precipitate when warmed with failings, and that leads us to think that M must therefore be an aldehyde, and we're told that N does not give that precipitate, and that then must mean that this is a ketone. And just as before, the exam question will give you the command to suggest structures for M and N, and this is just a case of now drawing two suitable chemicals, one being an aldehyde and the other one being a ketone. My advice here is to keep it simple if you possibly can, and here are the two structures. We've got a straight chain aldehyde, butan-al for M, and a straight chain ketone, butanone for N. And so to finish this whole video, just to remind you that there are two remaining functional group isomer pairs. There is the ester and the carboxylic acid, and we've just been through how you could prove that something was a carboxylic acid, and there is an alcohol and ether as the final pair, and we know how to prove something is an alcohol. Okay, so that's the end of this video, and that's the end of Year 1 Organic Chemistry. So check out any of those videos if you've missed some. Otherwise, we'll be back soon with more physical chemistry. So thank you for listening. Hope it's been useful. See you soon. Bye-bye.